This is what the numbers actually say about being alone in the galaxy, and why a growing number of scientists now think humanity might be the only intelligent civilization the Milky Way has ever produced. For more than 70 years, researchers have pointed telescopes and radio dishes at the sky, looking for a single confirmed signal from another technological species, and they have found nothing. Today, we're walking through the actual science behind that silence, starting with a lunchtime conversation in 1950, moving through the Drake equation, the WOW signal, the Great Filter, and the newest exoplanet data, all the way to what it would really mean if we turned out to be the only ones. Before we get into it, if you're the kind of person who lies awake wondering about this, go ahead and hit subscribe, because we dig into questions exactly like this one every week. The story starts at Los Alamos National Laboratory, sometime in the summer of 1950. Physicist Enrico Fermi was having lunch with a group of colleagues, and the conversation had drifted toward a recent wave of UFO reports and a New Yorker cartoon joking about aliens stealing trash cans. The group laughed it off, moved on to other topics, and then, seemingly out of nowhere, Fermi asked a question that nobody in the room could answer. He asked, "Where is everybody?" It sounds almost too simple to matter, but underneath that question was a piece of math that still hasn't been solved. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars, many of them far older than our own Sun, which is roughly 4.5 billion years old. If even a small fraction of those older star systems produced technological civilizations, and if any of those civilizations developed even modest rocket technology, the SETI Institute has pointed out that a civilization with a reasonable amount of interstellar ambition could spread across the entire galaxy in a matter of tens of millions of years. That sounds like an enormous stretch of time until you compare it to the age of the galaxy itself, which is roughly 1,000 times older than that. In other words, there has been more than enough time, over and over again, for someone to have already gotten here. And yet, when we look up, there's nothing. No radio chatter, no probes, no visitors, no unmistakable engineering scars on any star system we've ever observed. That gap between what the math predicts and what we actually see is what scientists now call the Fermi Paradox, and it has only gotten sharper as our tools have gotten better. To understand why this question carries so much weight, you have to understand just how big the numbers really are. Our galaxy alone holds an estimated 250 billion stars, and the observable universe beyond it contains something on the order of 70 sextillion stars, a number so large it barely means anything when you say it out loud. Even if intelligent life only develops around one star out of every million, or one out of every billion, simple multiplication says the Milky Way should still be home to a meaningful number of advanced civilizations. This is sometimes called the argument by scale, and it rests on an idea astronomers call the mediocrity principle, which basically says, Earth isn't special. Our Sun is an ordinary yellow dwarf star. Our position in the galaxy isn't unusual, and the physics and chemistry that produced life here should, in theory, be able to produce life anywhere the same ingredients and conditions show up. If that principle holds, the silence coming from the rest of the galaxy becomes very hard to explain. For most of human history, this was a purely philosophical question, because we had no way of even knowing whether planets existed around other stars. That changed dramatically over the last 3 decades. As of the most recent counts from NASA's Exoplanet Archive, astronomers have confirmed more than 6,000 exoplanets, worlds orbiting stars other than our own Sun. The archive itself was launched in December of 2011 by the NASA Exoplanet Science Institute, and it has been adding new confirmed worlds nearly every week since. A huge share of that growth has come from NASA's Transiting Exoplanet Survey satellite, known as TESS, which launched in April of 2018 and scans the brightest, nearest stars in the sky for the telltale dimming that happens when a planet crosses in front of its star. According to Scientific American, nearly half of the 1,000 exoplanets confirmed since 2022 were found by TESS alone, and NASA's Exoplanet Institute chief scientist, Jesse Christensen, has said the team expects the total count to reach 10,000 confirmed planets within just a few years. Before TESS, the heavy lifting was done by the Kepler Space Telescope, NASA's first mission built specifically to search for Earth-like worlds along with its successor mission K2. Even though Kepler stopped operating years ago, scientists are still combing back through its archived data and finding new planets hiding in the numbers. What all of this tells us is that planets are not rare. They are, if anything, the rule rather than the exception. Christensen put it simply when she said that every time astronomers turn on a new telescope and point it at the stars, they find planets, calling it, in her words, amazing. That single fact quietly dismantles one of the oldest objections to the idea of alien life, the assumption that planets themselves might be scarce. They aren't. The real mystery isn't whether other worlds exist. It's why, among all of those worlds, we haven't found a shred of evidence that any of them ever produced someone capable of saying hello back. Which brings us to the tool scientists have used for more than 60 years to try to put a number on all of this uncertainty, a formula called the Drake equation. Its story begins in April of 1960, when a young radio astronomer named Frank Drake was running Project Ozma at the National Radio Astronomy Observatory. Project Ozma pointed an 85-foot telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, tuning in to a frequency of 1,420 MHz, the exact frequency at which atomic hydrogen naturally emits radiation, on the theory that any civilization building radio telescopes would likely be listening on that same frequency too. Nothing came of it, but it planted a seed. The following year, in 1961, a member of the Space Science Board at the National Academy of Sciences asked Drake to organize a small conference on the search for extraterrestrial intelligence, to be held at the Green Bank Observatory in West Virginia. Drake ended up inviting around 10 people, and the guest list that showed up on November 1, 1961, was remarkable for how much talent was packed into one room. It included physicist Philip Morrison, chemist Melvin Calvin, who would go on to win a Nobel Prize, and a 27-year-old postdoc who was, at the time, the least famous person in the building, a young astronomer named Carl Sagan. To give the three-day meeting some structure, Drake sat down beforehand and worked out a way to organize the discussion, and on the morning the conference opened, he walked up to a chalkboard and wrote out 7 letters strung together into an equation: n equals r star times f sub p times n sub e times f sub l times f sub I times f sub c times l. Drake meant it only as a discussion outline, something to structure a few days of conversation among a dozen scientists. Instead, it became one of the most famous formulas in the history of science, sometimes described as the second most famous equation in the world. Each letter stands for a piece of the puzzle. R star is the rate at which new stars form in the galaxy each year. F sub p is the fraction of those stars that have planets. N sub e is the average number of planets in a system that could actually support life. F sub l is the fraction of those planets where life actually gets started. F sub I is the fraction of those where life evolves into something intelligent. F sub c is the fraction of intelligent species that develop the technology to send detectable signals into space. And L, the final and most debated term, is the average length of time such a civilization survives and keeps transmitting before it either destroys itself or falls silent for some other reason. Multiply all 7 together and, in theory, you get n, the number of civilizations in our galaxy we might actually be able to detect right now. At the time of that first meeting, only one of those 7 numbers had any real observational backing, the star formation rate, which was estimated at around 1 new star per year. Every other term was, in Drake's own words, largely guesswork. Astrobytes, a publication written by astronomy graduate students, has noted that back in 1961, no exoplanets had ever been confirmed, so the fraction of stars with planets was pure theory, and Drake estimated the number of habitable planets per system at somewhere between 2 and 3, based purely on what our own solar system looked like. 60 years later, according to the SETI Institute, we've barely closed the gap. Thanks to the discovery of thousands of exoplanets since the mid-1990s, scientists now have solid numbers for the fraction of stars with planets, and a rough sense of how many of those planets sit in a habitable zone. But the equation's last 3 terms, the odds that life starts, the odds it becomes intelligent, and the odds an intelligent species survives long enough to be noticed, remain almost exactly as uncertain today as they were in that room in Green Bank in 1961. And it's that final term, L, the lifespan of a civilization, that historians of science say caused the most heated argument at the original meeting, because it's the one number that isn't really about biology or physics at all. It's about whether intelligent species tend to survive their own success. It's worth pausing to look at exactly how far astronomers have actually gotten on those first few terms of Drake's equation, because the progress has been real, even if it hasn't come close to resolving the argument. Astronomers refer to the fraction of Sun-like stars that host a roughly Earth-sized planet sitting inside the habitable zone, using a shorthand term, eta Earth, and pinning that number down was one of the central goals of the Kepler mission from the moment it launched. The results have shifted around somewhat, depending on exactly how researchers define the habitable zone and what counts as Earth-sized. But they've consistently pointed in the same direction, toward a universe where planets like ours are common rather than exceptional. A 2013 study using early Kepler data estimated eta Earth at somewhere between 1.1 and 2.8%. A later 2013 analysis, using a different definition of the habitable zone, put the figure at roughly 22% of all Sun-like stars in the galaxy. By 2020, a full retrospective analysis of the complete Kepler dataset, described by NASA's Kepler mission scientists, concluded that there are at least 300 million Earth-sized planets sitting in the habitable zones of Sun-like stars across the Milky Way, with researchers involved in the study noting that the true number could be considerably higher than that conservative floor. And in a more recent NASA-led analysis, factoring in more sophisticated modeling of how a planet's atmosphere affects its actual surface temperature, researchers estimated that a conservative 50% of Sun-like stars host a rocky planet capable of holding liquid water on its surface, with an optimistic version of the same habitable zone definition pushing that figure as high as 75%. Sit with that for a second. 300 million planets, at an absolute conservative minimum, sitting in the right temperature zone around stars similar to our own Sun, just within our own galaxy, and that number doesn't even count the potentially habitable worlds orbiting the much more common red dwarf stars, the kind of star that TRAPPIST-1 happens to be. This is the part of the Drake equation that has actually been answered with real data, 60 years after Frank Drake first guessed that the number of habitable planets per star system might be somewhere around 2 or 3, based on nothing more than a glance at our own solar system. His original guess, it turns out, wasn't far off, and if anything, the newer, harder data suggests he may have actually underestimated how common these worlds really are. And that's exactly what makes the silence so much harder to explain than it might have seemed in 1961. Back then, a skeptic could reasonably argue that maybe planets themselves were rare, that maybe Earth really was some kind of cosmic anomaly simply for having a planet to live on at all, and that this alone might account for why we hadn't heard from anyone. That argument no longer holds up, with genuine, hard-won observational data now pointing to hundreds of millions of Earth-sized, temperate worlds scattered across our own galaxy alone. The mystery has been squeezed down into an increasingly narrow and increasingly uncomfortable space. It's no longer a question of whether the raw material for life is out there. It clearly is, in staggering abundance. The entire weight of the Fermi Paradox now rests on the three hardest, least understood, least measurable terms in Drake's original equation: the odds that life actually starts on one of those hundreds of millions of worlds, the odds that it becomes intelligent if it does, and the odds that intelligence survives long enough, once it exists, to build something capable of reaching out across the dark and being heard. There's one more dimension to all of this worth adding, before pulling everything together, and it's easy to overlook, because most explanations for the Fermi Paradox focus entirely on space, on distance, on where a civilization might be hiding, while quietly ignoring an equally important variable: time. The Milky Way galaxy is roughly 13.6 billion years old. Human beings, in our current anatomically modern form, have existed for something like 200,000 years, and we've only been capable of broadcasting or detecting radio signals for a little over a century. Set those two numbers side by side, and the comparison becomes almost absurd. A century of radio capability against 13.6 billion years of galactic history works out to a sliver of time so thin it barely registers. something on the order of 100 millionth of the galaxy's full lifespan. If other technological civilizations, anywhere in the Milky Way's long history, have gone through a similar pattern, existing as a radio-capable, detectable civilization for only a few thousand or a few million years, before falling silent, whether through self-destruction, a deliberate choice to stop broadcasting, or some kind of technological transition into something we wouldn't even recognize as a civilization anymore, then the odds of any two such narrow windows actually overlapping, close enough in both time and space to notice each other, could be extraordinarily small, even in a galaxy that has hosted a genuinely large number of civilizations across its full history. This reframing has a strange, double-edged quality to it, because it cuts in two completely different directions at once, depending on how you look at it. On one hand, it offers a genuinely less alarming alternative to the darker interpretations of the Great Filter. If most civilizations simply miss each other because of timing rather than because something is actively destroying them, then the silence stops being evidence of some galaxy-wide catastrophe and becomes something closer to bad luck, a scheduling problem played out across billions of years, rather than a warning sign about our own future. On the other hand, this same timescale argument opens up a genuinely striking possibility that gets far less attention than it probably deserves. The idea that humanity might not be late to the party at all, but early. Building a rocky, Earth-like planet capable of supporting complex life requires more than just the right star and the right orbit. It requires a galactic environment that has already been enriched over billions of years of previous star formation and supernova explosions, with enough heavy elements like carbon, oxygen, and iron to build a planet like ours in the first place. Some researchers studying the chemical evolution of the galaxy over time have pointed out that this enrichment process is still ongoing, meaning the universe may, right now, still be in a comparatively early phase of producing the raw ingredients needed for rocky, Earth-like planets to form in large numbers. If that's true, the silence surrounding us might not mean life is rare, or doomed, or hiding. It might simply mean that most of the galaxy's technological civilizations, the ones that will eventually exist around stars still forming right now, haven't been born yet, and that Earth, against every intuition built from a species that assumes it's arriving late to an ancient, crowded party, might actually be one of the very first guests to show up. Physicist Michael Hart, whose 1975 paper is now recognized as the first formal, technical treatment of what would later become known as the Fermi Paradox, actually organized possible explanations into four broad categories back then. Physical explanations, where interstellar travel simply turns out to be too difficult for anyone to manage. Sociological explanations, where advanced civilizations make a collective choice toward isolation. Observational explanations, where evidence of visitation exists but has somehow gone unnoticed or unrecognized. And temporal explanations, the category this section has been building toward, where simply not enough time has passed for paths to cross. 50 years after Hart first laid out that framework, none of those four categories has been ruled out, and none has been confirmed either. What the timescale argument adds isn't a solution, it's a genuinely humbling reminder that when a search has been running for barely a century against a backdrop stretching back nearly 14 billion years, describing the results as inconclusive isn't a disappointment. It's simply an accurate description of how early in the process we still are. Before we go further, it helps to have a way of actually measuring what an advanced civilization would look like, because the search for extraterrestrial intelligence isn't just about listening for a voice, it's about knowing what kind of footprint that voice would leave behind. In 1964, Soviet astrophysicist Nikolai Kardashev proposed exactly that kind of measuring stick, a framework now known as the Kardashev Scale, which ranks civilizations not by how smart they are or how advanced their culture is, but by a single, brutally practical metric: how much energy they can actually harness and use. Kardashev's reasoning was that energy is the currency behind everything a civilization does: building, moving, computing, communicating, and that the amount of energy a species commands tells you more about its reach than almost anything else you could measure. He laid out 3 tiers. A Type 1 civilization, sometimes called a planetary civilization, has learned to harness essentially all of the energy available on its home world, something on the order of 10 to the 16th or 10 to the 17th watts. A Type 2 civilization, a stellar civilization, has scaled up to capture the entire energy output of its home star, a jump of roughly 10 billion times, which Kardashev speculated would likely require building some kind of massive structure encircling the star itself, an idea later popularized as a Dyson sphere. And a Type 3 civilization, a galactic civilization, has scaled up again by another factor of roughly 10 billion, harnessing the combined energy output of an entire galaxy's worth of stars, something on the order of 10 to the 36th or 10 to the 37th watts. Where does that leave us? According to an extension of the scale credited to Carl Sagan, present-day humanity sits at roughly 0.73 on the Kardashev scale, meaning we haven't even finished becoming a Type 1 civilization yet. We currently consume something on the order of 18 terawatts of primary energy globally, and to become a true Type 1 civilization, fully harnessing everything our own planet has to offer, we'd still have a considerable distance left to travel. Type 2 and Type 3 remain almost impossible to picture in any concrete way. A Type 2 civilization would have functionally unlimited energy for planetary-scale engineering, moving asteroids, terraforming entire worlds, running computation at a scale that could simulate a planet's climate in real time. A Type 3 civilization, harnessing the output of hundreds of billions of stars across a galaxy, would be operating on a scale so far beyond human experience that scientists studying it say the very idea becomes conceptually strange, given that even communication at the speed of light between opposite sides of such a civilization could take tens of thousands of years. The Kardashev scale matters for the Fermi Paradox because it tells us exactly what to look for. A Type 2 or Type 3 civilization wouldn't just be sending out radio signals for us to notice. According to Kardashev's own calculations, comparing detection odds across the different tiers, spotting a Type 1 civilization from another star system would be extraordinarily difficult, but a Type 2 or Type 3 civilization would be capable of transmitting enormous quantities of information across vast distances, and more importantly, it would leave a physical signature. A civilization capable of building structures around its own star, or around many stars across a galaxy, should show up in astronomical surveys as unusual infrared emission, waste heat radiating off a megastructure that's blocking or capturing a star's visible light. Some researchers have even proposed that a true Type 3 civilization would leave a mark visible across cosmological distances, suppressing a galaxy's ordinary starlight and replacing it with an unmistakable infrared glow. Astronomers have actually gone looking for exactly that signature, scanning galaxy catalogs for anything showing an unusual excess of infrared light that couldn't be explained by ordinary star formation or dust. They haven't found one. Not a single galaxy in our observable neighborhood shows the kind of energy signature a Type 2 or Type 3 civilization would be expected to leave behind, which is itself a data point, a very large, very quiet one, sitting right alongside everything else the Fermi Paradox has to explain. It's worth being upfront about the limits of Kardashev's framework too, because critics have pointed out a real weakness in it. The scale is built entirely around a sample size of exactly one civilization, our own, and it assumes that any sufficiently advanced species would follow a broadly similar trajectory toward maximizing energy consumption. That might not be true at all. An advanced civilization might choose a fundamentally different path, one focused on efficiency rather than expansion, or on some kind of internal, computational, or even virtual existence that doesn't require swallowing a star's worth of energy to sustain itself. Critics have called this assumption a form of terrestrial chauvinism, the idea that we're measuring alien ambition using a ruler built entirely out of human assumptions about growth and conquest. Still, even with that caveat, the Kardashev scale gives us something concrete to search for, and the fact that we've found no trace of anything above our own primitive rung, anywhere, is one more thread woven into the same overall silence. The Kardashev scale gave scientists a specific signature to search for, a Dyson sphere or some equivalent megastructure showing up as unusual infrared waste heat around a star, and in 2015, astronomers thought, for a genuinely exciting stretch of time, that they might have actually found a candidate. A team led by Yale astronomer Tabetha Boyajian had been sifting through data from the Kepler Space Telescope when they noticed something strange coming from a star called KIC 8462852, quickly nicknamed Tabby's star, or sometimes Boyajian star, sitting roughly 1,280 light-years from Earth. Ordinary planetary transits, the kind Kepler was specifically built to detect, dim a star's light by a small, consistent, and predictably periodic amount, usually around 1%. Tabby's star wasn't behaving anything like that. Its brightness dipped by as much as 22% at completely irregular intervals, far too large and far too erratic to be explained by any known planet, and additional analysis found the star had also dimmed gradually and steadily by roughly 20% across an entire century, comparing modern observations against archival photographic plates dating back to 1890. Nothing about the pattern matched any previously catalogued astronomical phenomenon, and when researchers, including astronomer Jason Wright, who has written extensively about how a Type II Kardashev civilization might actually be detected, took a serious look at the data, they concluded that Tabby's star was a genuinely strong candidate, worth investigating specifically for signs of an artificial megastructure, something like a partially completed Dyson sphere, intermittently blocking large sections of the star's light as pieces of it passed across the stellar disk. The excitement, understandably, spread well beyond the scientific community, and for a couple of years, Tabby's star became one of the most talked-about objects in the entire sky. But careful, patient follow-up observations gradually dismantled the megastructure hypothesis piece by piece. The first serious blow came from searches for the specific infrared signature that a Dyson sphere or any large orbiting structure should produce. The same waste heat signal astronomers have used in broader surveys looking for Kardashev Type II civilizations. And none of that expected infrared glow ever showed up around Tabby's star. Then, in 2017 and 2018, researchers led by Boyajian herself, using ground-based telescopes and contributions from amateur astronomers around the world who helped catch the star in the act of dimming in real time, found the decisive piece of evidence. They discovered that the star dimmed by different amounts at different wavelengths of light, more in ultraviolet than in infrared. A solid, opaque object, whether a planet, a fragment of a shattered world, or an artificial structure built by an advanced civilization, would block all wavelengths of light equally, the same way an eclipse doesn't change color as it happens. What the data actually showed was consistent with something far more mundane, an uneven, orbiting cloud of ordinary dust, with individual particles smaller than the wavelength of visible light itself, arranged in something like an irregular ring with a rough 700-day orbital period. Huan Meng, the University of Arizona astronomer who led one of the key follow-up studies, put it directly, stating that the wavelength-dependent nature of the dimming essentially ruled out the megastructure explanation, since an artificial object simply couldn't produce that particular pattern. Tabby's star never turned out to be aliens, and by the time later studies using NASA's Spitzer and Swift missions confirmed the dust cloud explanation, most of the scientific community had already moved on from the megastructure hypothesis entirely. But the whole episode is worth remembering for exactly what it demonstrates about how this entire field actually operates. A strange, unexplained signal showed up in real data. Scientists didn't dismiss the most exciting possible explanation out of hand, but they also didn't rush to announce it as a discovery. They designed follow-up observations specifically capable of distinguishing between a natural explanation and an artificial one. They waited for the data those observations required, and when the evidence pointed toward dust rather than a Dyson sphere, they said so plainly and moved forward. It's the same basic process that has since played out with the K2-18b biosignature claim, and the same process now underway with the WOW signal's proposed magnetar explanation. None of these individual mysteries has turned out to be the discovery everyone hoped for, but each one has, in its own way, sharpened exactly what real evidence for another civilization would actually have to look like, and made the search a little bit better at telling the difference between a genuine signal and an oddly ordinary corner of the universe. That uncertainty is exactly what makes one night in August of 1977 so hard to forget. By then, Ohio State University had been running its own search for extraterrestrial intelligence for years, using a massive radio telescope known as the Big Ear, a structure spread across 3 acres of farmland in Delaware, Ohio. The project had actually started as something else entirely, a wideband radio sky survey, that catalogued around 20,000 radio sources before Congress pulled its funding through the National Science Foundation in 1973. Rather than shut the telescope down, the team repurposed it to hunt specifically for narrowband signals, the kind of tight, artificial-looking radio frequencies you'd expect from a broadcast rather than from a star or a gas cloud. On the night of August 15, 1977, at around 11:16 p.m. Eastern Time, the telescope picked something up. Nobody noticed it happen in real time. It was the following morning when a volunteer astronomer named Jerry Eman sat down with a stack of paper printouts to review the previous day's data. Each line on the printout represented 10 seconds of observation, and the intensity of any signal was measured on a scale from 0 to 9, and then continuing through the letters A through U, with U representing a signal 30 times stronger than the lowest reading. As Eamon scanned down the page, he hit a sequence that jumped out immediately. 6, E, Q, U, J, 5. It was, by a wide margin, the strongest and most unusual reading anyone on the project had ever recorded. Eamon circled it in red pen and, right there in the margin, wrote a single word: wow. The signal lasted 72 seconds, rising in strength for the first 36 seconds, and then fading for the next 36, which is exactly the pattern you'd expect from something crossing through a fixed telescope's field of view as the sky rotated overhead, rather than a passing satellite or a piece of ground-based interference. It arrived at a frequency of roughly 1,420 MHz, within a fraction of a percent of the hydrogen line, the same frequency Frank Drake had chosen for Project Ozma 17 years earlier, and a frequency that international agreements actually protect from terrestrial broadcasting for exactly this reason. Robert Dixon, who directed the Ohio SETI program at the time, said something at the time that has stuck with the story ever since. Some people, he said, think the whole search is baloney, but once a signal is found, it means something is out there, and it becomes, in his words, the plum of the century. The trouble is, nobody has ever found that signal again. Astronomers have pointed telescopes at that same patch of sky in the constellation Sagittarius again and again over the decades, including modern follow-up searches conducted by the Breakthrough Listen project, and the result has been silence every single time. The Big Ear telescope itself was dismantled in the late 1990s after the 22-year Ohio SETI program wrapped up, which researchers describe as the longest continuously running search for extraterrestrial intelligence ever conducted. To this day, the WOW signal remains the strongest single candidate humanity has ever recorded for an artificial transmission from beyond Earth, and to this day, nobody can say for certain what it actually was. That single unrepeated signal captures the entire Fermi Paradox in miniature. For 72 seconds, something matched exactly what scientists were listening for, and then it vanished into a silence that has now lasted almost 50 years. And that silence is what pushed economist Robin Hanson, in 1996, to propose one of the most unsettling explanations anyone has offered for why the galaxy looks the way it does. Hanson published an essay titled "The Great Filter, Are We Almost Past It?" And in it, he laid out an argument that strips away a lot of the science fiction romance around the search for alien life and replaces it with something closer to a warning. His reasoning goes like this: somewhere between lifeless chemistry on a young planet and a civilization capable of expanding across the galaxy, there has to be at least one step that is extraordinarily unlikely, a bottleneck so narrow that almost nothing manages to pass through it. Hanson called that bottleneck the Great Filter. If the filter is real, and the fact that the galaxy appears dead and silent everywhere except right here on Earth suggests that it is, then the only real question left is where that filter sits along the timeline. Is it somewhere behind us, meaning humanity has already beaten the odds and made it through the hardest part? Or is it somewhere ahead of us, meaning every civilization that reaches roughly our level of technology eventually runs into the same wall and never makes it any further? The difference between those two possibilities is not a small one. As Hanson himself put it, humanity seems to have a bright future, meaning a real chance of expanding out and filling the universe with lasting life. But the fact that space around us looks completely dead right now tells us that any given clump of matter faces an extremely low chance of ever reaching that future. If the filter already sits behind us, in some rare fluke of chemistry or evolution that happened here on Earth and almost nowhere else, then we should actually feel somewhat reassured, because it would mean the hardest part is already finished. But if the filter is still ahead, waiting somewhere between where we are now and where a truly spacefaring civilization would need to be, then the fact that we can't see anyone else out there stops being comforting and starts looking like evidence, a kind of cosmic pattern showing that species like us tend not to make it much further than this. Hansen didn't pretend to know which scenario is true, and neither does anyone else, but he was blunt about the stakes. If we can't find the great filter somewhere in our past, he wrote, we will have to fear it somewhere in our future. So where might that filter actually be? Scientists who study this question generally break the problem into two broad possibilities, an early filter or a late one. And the case for an early filter starts with just how difficult it apparently was for life on Earth to get anywhere at all. The oldest confirmed evidence for life on this planet, in the form of fossilized stromatolites, dates back roughly 3.5 billion years, and simple single-celled organisms without a nucleus were the only form of life on Earth for an extraordinarily long stretch of time after that. It took until somewhere between 2 and 2.1 billion years ago, well over a billion years later, for the first eukaryotic cells to appear, cells complex enough to contain a nucleus and internal structures. And multicellular life, organisms actually made of more than one cooperating cell, didn't show up until somewhere around 1.2 to 1.6 billion years ago, depending on which fossil evidence you're weighing. Add it all up and you get a picture where, for roughly 3 billion years out of Earth's 4.5 billion year history, nothing more complicated than a single cell existed anywhere on the planet. It wasn't until around 541 million years ago that the Cambrian explosion produced the sudden burst of complex, differentiated animal life that eventually led, after hundreds of millions of additional years of evolution and repeated near-total extinction events, to something capable of building a radio telescope. Every one of those transitions, from lifeless chemistry to a single self-replicating cell, from simple cells to complex ones, from solitary cells to cooperating multicellular organisms, from simple animals to intelligence itself, is a candidate for where the great filter might sit. If any one of those steps turns out to be astronomically unlikely, something that might only happen once in every trillion planets that otherwise looks just like Earth, then it would neatly explain why the galaxy is quiet, without requiring anything to have gone wrong for humanity specifically. It would simply mean we got lucky, and we're one of the vanishingly small number of places where the dice landed right. This is the reasoning behind what's known as the rare Earth hypothesis, an idea that takes the mediocrity principle Fermi's paradox depends on and turns it upside down. Instead of assuming Earth is a typical, unremarkable planet, the rare Earth hypothesis argues that Earth might actually be sitting out on the far tail of a statistical distribution, an unusually fortunate result, rather than a representative one. Supporters of this view point to the sheer number of conditions that had to line up correctly here. A planet doesn't just need to sit in a star's habitable zone, the region where liquid water could theoretically exist on the surface. According to researchers writing about the paradox, it also needs long-term stellar stability, meaning a star that doesn't flare violently or change brightness dramatically over billions of years. It needs a substantial atmosphere to regulate temperature and block harmful radiation. It needs a protective magnetic field, generated by a molten metallic core, to shield the surface from solar wind. And it needs plate tectonics, the slow grinding of continental plates against each other, which recycles carbon and other volatile elements through what's called the carbonate-silicate cycle, a process that has kept Earth's climate within a survivable range for billions of years running. Every one of those requirements is its own opportunity for failure, and the rare Earth hypothesis argues that when you multiply enough of these independent conditions together, even if each one individually seems fairly likely, the odds of getting a planet that checks every box at once can collapse into something vanishingly small. Before life could take 3 billion years to crawl from single cells to complex ones, it first had to start at all, and that first spark turns out to be its own deep unknown, one that scientists have been chipping away at since the early 1950s. In 1952, a 22-year-old graduate student at the University of Chicago named Stanley Miller approached his advisor, the chemist Harold Urey, with an idea for an experiment that would test whether the basic organic building blocks of life could form on their own, without any living thing involved at all, purely through ordinary chemistry and physics, acting on a lifeless planet. The experiment, run in 1952 and published in 1953, was built around a sealed glass apparatus containing water vapor, methane, ammonia, and hydrogen, an approximation of what scientists at the time believed Earth's early atmosphere looked like, sitting above a flask of water meant to represent an ocean. Miller ran an electrical spark through the gas mixture continuously for about a week, simulating the lightning that would have crackled across a young, violent Earth, and then analyzed what had collected in the water below. The results were striking. The experiment had produced amino acids, the fundamental building blocks that combine to form proteins, generated entirely from simple, lifeless ingredients. The finding became one of the most cited pieces of evidence in all of origin of life science, and it's still taught in science classrooms around the world today as a foundational demonstration that the chemistry of life could plausibly have assembled itself on a young, sterile planet. The Miller-Urey experiment answered one question while leaving several much harder ones completely untouched, and scientists studying the origin of life have been upfront about that gap ever since. Producing amino acids is a meaningful first step, but amino acids are not by themselves alive. Getting from a flask of loose amino acids to a self-replicating, information-carrying molecule like RNA or DNA, and then from there to an actual functioning cell capable of maintaining itself, repairing damage, and reproducing, remains one of the largest unsolved problems in biology. Researchers have proposed a range of possible settings for that next leap, including something closer to home than a lightning-struck ocean surface. Deep beneath Earth's oceans, at hydrothermal vents where mineral-rich, superheated water pours out of the seafloor into freezing darkness, life today thrives entirely without sunlight, and a number of researchers have argued that environments like these, chemically active, energy-rich, and shielded from the harsh ultraviolet radiation that would have bathed early Earth's surface, are a more plausible cradle for life's actual origin than the open water Miller and Urey simulated in their original glassware. The debate over exactly where and how that first transition happened remains unresolved, and it sits at the very base of every other question this video has covered. If getting from simple chemistry to the first living cell turns out to be a comparatively easy, near-inevitable step, once the right raw ingredients and energy sources are present, that pushes hard against the idea that Earth got extraordinarily lucky. But if that step turns out to be the rarest, hardest transition of them all, harder even than the billion-year climb from simple cells to complex ones, then the great filter Robin Hanson described in 1996 might not be hiding somewhere in our future at all. It might be sitting at the very first page of the story, in the transition from lifeless rock to the first strand of self-replicating chemistry, a threshold Earth happened to cross once, roughly 3.5 to 3.8 billion years ago, and which, for all we currently know, almost nothing else in the galaxy ever has. One more piece of Earth's specific luck deserves real attention here, because it might be one of the most underrated items on the entire rare Earth list, and it has nothing to do with our sun or our position in the galaxy at all. It's our moon. The leading scientific explanation for how the moon formed is called the giant impact hypothesis, which holds that roughly 4.5 billion years ago, not long after Earth itself finished forming, a Mars-sized protoplanet that researchers have nicknamed Theia collided with the young Earth at a glancing, oblique angle. The impact was violent enough to melt large portions of both bodies, blasting a ring of debris into orbit around Earth that gradually coalesced into the Moon over a relatively short span of time afterward. Evidence supporting this theory has piled up steadily, including a striking similarity between the oxygen isotopes found in Earth rock and in samples of Moon rock brought back by Apollo astronauts, along with the fact that Moon rock is dry and depleted of certain elements that would have evaporated away under the kind of extreme heat a violent collision would have generated. What matters most for the rare Earth argument isn't how the Moon formed, though. It's what the Moon has done for Earth ever since. Its gravitational pull actively stabilizes Earth's axial tilt, currently locked in at roughly 23.5 degrees. And researchers who model planetary dynamics have found that without a large moon acting as a stabilizing anchor, gravitational interactions between Earth, the Sun, and the outer planets, especially Jupiter, would cause our planet's tilt to drift chaotically over millions of years. That kind of chaotic tilting would mean wildly unpredictable seasons and extreme, unstable climate swings, exactly the kind of environment that makes it far harder for complex land-based life to establish itself and evolve continuity across the long stretches of geologic time evolution actually requires. Earth's own geologic record backs this up. Scientists studying an 850 million-year-old fossilized stromatolite, one of the oldest and most direct pieces of physical evidence of ancient life, found that its growth pattern, shaped by its orientation toward the midday sun, is consistent with an axial tilt of roughly 26.5 degrees at the time, remarkably close to the 23.5-degree tilt Earth holds today, suggesting that whatever stabilizing effect the Moon has been providing has held remarkably steady for the better part of 1 billion years. Some researchers who study the giant impact hypothesis have gone further and connected it directly to the rare Earth argument itself. They point out that the specific combination required, a Mars-sized body striking a young Earth at exactly the right glancing angle and exactly the right velocity to eject enough material to form a large, stabilizing moon without simply obliterating the planet outright, represents an extraordinarily narrow set of physical conditions. Get the angle slightly wrong, or the impactor's size slightly wrong, and you either get no moon at all, a moon too small to meaningfully stabilize anything, or a collision violent enough to destroy the young planet's chances at hosting life altogether. Some scientists studying planet formation across the galaxy have proposed that giant impacts of this general kind may actually be common events during a solar system's early, chaotic formation period, which is genuinely reassuring for the odds of an Earth-like moon existing elsewhere, but common enough to reliably produce a moon of exactly the right size, in exactly the right orbit, stabilizing exactly the kind of axial tilt that allows billions of years of relatively stable seasons rather than chaotic climate swings, is a much narrower and much less certain question, and it's one more item on the long, quiet list of coincidences that had to line up correctly for a planet like ours to end up producing something capable of asking one lunchtime in 1950, where everybody else actually is. There's one more layer to the rare Earth argument, and it operates at a scale even larger than the planet itself, larger even than the solar system. It's not enough to have the right star and the right planet. According to a growing body of research, you also need to be located in the right part of the galaxy entirely. The concept is called the Galactic Habitable Zone, and it was first introduced in a 2001 paper by astronomer Guillermo Gonzalez, extending the familiar idea of a stellar habitable zone, the temperature band around a star where liquid water can exist, out to the scale of the entire Milky Way. A landmark 2004 study, published in the journal Science, led by astrophysicist Charles Lineweaver, modeled the galaxy's history and identified the galactic habitable zone as a ring-shaped region, an annulus, sitting between roughly 7 and 9 kiloparsecs from the galaxy's center, meaning somewhere in the neighborhood of 23,000 to 29,000 light-years out, gradually widening over time as the galaxy has aged and evolved. The reasoning behind drawing that boundary works from both directions at once. Toward the galactic center, conditions get genuinely hostile. Stars are packed far more densely together near the Milky Way's core, and that crowding brings with it a dramatically higher rate of supernova explosions, gamma-ray bursts, and other violent high-energy events, along with more frequent close encounters with passing stars and molecular clouds capable of disrupting a young planetary system entirely or bombarding a planet with lethal radiation from a relatively short astronomical distance away. As NASA's own visualization materials on this topic describe it, planets closer to the galactic center might actually form more easily, since that region is rich in the heavier elements needed to build rocky worlds. But any life trying to survive there would also be sitting in a much more dangerous neighborhood, regularly flooded with radiation from densely packed and often massive, short-lived stars. Move too far in the opposite direction, out toward the sparse outer edges of the galaxy, and the opposite problem takes over. Heavier elements, The same carbon, silicon, and iron that make rocky planets possible in the first place become steadily scarcer the farther out you go, because those elements are forged inside stars and then scattered by supernova explosions, and the outer galaxy simply hasn't had as many generations of star formation and stellar death to build up that same chemical enrichment. The galactic habitable zone sits in the calm, comparatively well-stocked middle ground between those two extremes, and Lineweaver's 2004 study found something else worth noting: that fully 75% of the stars sitting inside that zone are actually older than our own Sun, meaning that whatever advantage Earth has enjoyed by having billions of years of relatively stable time to develop complex life, plenty of other star systems in the same galactic neighborhood have had just as much time, or more, to do the exact same thing. It's worth being upfront that the galactic habitable zone concept, like nearly every other framework in this video, has real critics. Researchers have pointed out that it's genuinely difficult to precisely quantify exactly how dangerous a given region of the galaxy actually is, and more recent computer simulations of galactic dynamics have shown that stars don't simply stay parked in one orbit around the galactic center for their entire lifetimes. They can migrate substantially inward or outward over billions of years, which complicates the entire idea of treating any single galactic neighborhood as permanently safe or permanently hostile. Different research teams studying the question since Lineweaver's original 2004 paper have proposed meaningfully different boundaries for where the zone actually sits, with some models placing the safest region much farther out than others. Even with all of that genuine uncertainty, the underlying idea has held up reasonably well as one more item on the long list of specific conditions that had to align for a planet like Earth to spend 4.5 billion years developing life without getting sterilized by a nearby supernova or stripped of its atmosphere by a wandering rogue star. One more quiet, easily overlooked stroke of location that, alongside a stable sun, a well-timed moon, and a rare set of geological and chemical coincidences, helped produce the only civilization in this galaxy we currently know for certain actually exists. All of this discussion about the Great Filter and the rare Earth hypothesis rests on one underlying assumption: that life on any given planet has to originate there, from scratch, using only the raw chemistry available locally. There's an older and stranger idea that challenges that assumption directly, called panspermia, the hypothesis that life, or at least the building blocks of life, might not need to originate on a planet at all, but could instead be transported between worlds, seeded from one location to another across the vacuum of space itself. The idea has a surprisingly long history. Scottish physicist Lord Kelvin proposed as early as the 1800s that microorganisms encased inside meteorites might be able to survive a journey through space, and the Swedish chemist Svante Arrhenius later expanded on the concept, proposing a version called radiopanspermia, in which microscopic spores could be pushed across interstellar distances by nothing more than the physical pressure of starlight itself. For most of the 20th century, mainstream scientists treated the whole idea with real skepticism, and the concept didn't gain serious traction again until astronomer Fred Hoyle and mathematician Chandra Wickramasinghe revived it roughly 30 years ago. The central objection to panspermia has always been survivability. Space is about as hostile an environment as exists anywhere, a vacuum filled with intense radiation and temperature swings that would kill nearly anything almost instantly. But research into a category of organisms called extremophiles, life forms that thrive in conditions once assumed to be completely uninhabitable, has quietly chipped away at that objection over the past 2 decades. The clearest example is the tardigrade, sometimes called a water bear, a microscopic 8-legged animal that has become something of a mascot for the entire field. In 2007, researchers actually sent live tardigrades into low Earth orbit, exposing them directly to the vacuum and radiation of open space with no protective shielding at all. And when the samples were returned to Earth, some of the tardigrades were still alive. Studies have found that tardigrades can survive temperatures ranging from nearly absolute zero up to roughly 300 degrees Fahrenheit, pressures several times greater than those found in the deepest ocean trenches, and radiation doses hundreds of times higher than what would be lethal to a human being. largely through a process called cryptobiosis, in which the organism essentially shuts down its own metabolism and loses almost all of its internal water content, becoming, for all practical purposes, biologically inert until conditions improve. Other extremophiles have shown similarly startling resilience. A bacterium called Deinococcus radiodurans, nicknamed Conan the bacterium by researchers, can survive radiation doses that would kill nearly every other known organism many times over, and long-duration experiments run aboard the International Space Station, exposing dried microbial samples to the outside environment for as long as 3 years at a stretch, have shown that sufficiently shielded, aggregated colonies of certain bacteria can survive extended direct exposure to space. None of this proves that panspermia actually happened, and researchers studying the field are careful to point that out. What it does show is that the physical barrier, once assumed to make interplanetary or interstellar transport of life essentially impossible, isn't nearly as absolute as scientists once believed. A related and more specific version of the idea, called lithopanspermia, focuses on the transfer of life-bearing rock between planets within the same solar system, using material blasted into space by asteroid or comet impacts. This isn't purely theoretical either. Scientists have identified meteorites found here on Earth that originated on Mars, ejected by ancient impacts, and eventually landing on our planet millions of years later, and a study published in 2000 concluded that a Martian rock recovered on Earth stayed cool enough during its violent ejection and its fiery descent through our atmosphere that any microorganisms hitching a ride inside it could plausibly have survived the entire trip. It's worth being clear about what panspermia does and doesn't explain. It offers a possible mechanism for how life might spread once it exists somewhere, but it doesn't answer the harder question of how life got started in the first place. It just moves that question to wherever the life originally came from. Still, if it turns out to be even partially true, it would complicate the entire rare earth argument in an interesting way, suggesting that life, once it manages to get a foothold anywhere in a given solar system or star cluster, might be able to spread far more easily than a strictly earthbound view of biology would ever suggest. It's worth being honest about where the science actually stands today, because it's genuinely split. The argument by scale, the sheer number of stars and now confirmed planets, still pushes hard in the direction of thinking intelligent life should be common. The rare Earth hypothesis, along with the Great Filter, pushes back in the other direction, suggesting that number crunching alone can be misleading if it ignores just how many independent conditions have to be satisfied at once. Neither side has the kind of evidence that would settle the argument, which is exactly why the search continues, and why it's actually more active right now than at almost any point in its history. There's another argument connected to the Fermi Paradox that doesn't rely on radio signals at all, and it comes from thinking about machines instead of civilizations. The mathematician John von Neumann spent part of his career studying the theoretical possibility of self-replicating machines, devices capable of building exact copies of themselves given the right raw materials. Von Neumann never applied that idea to spacecraft directly, and he died of cancer in 1957, before anyone else did either. It was the astronomer Ronald Bracewell who first suggested, in 1960, that a self-replicating machine could be used to explore the galaxy, and it was physicist Frank Tipler who, in 1981, pushed the idea to its logical extreme and used it to make a genuinely striking argument. A so-called von Neumann probe, in Tipler's formulation, would be an unmanned, self-replicating spacecraft that could travel to a neighboring star system, land on a suitable moon or asteroid, mine the raw materials it needed, and construct several copies of itself. Those copies would then launch outward in different directions and repeat the process. And because the growth is exponential rather than linear, the numbers involved multiply extremely fast. Researchers who have modeled this kind of expansion have calculated that even using rocket technology available back in 1980, technology far below what a civilization even a few hundred years more advanced than us would likely possess, a wave of von Neumann probes could explore and colonize an entire galaxy the size of the Milky Way in well under 300 million years. Set against the roughly 13 billion-year history of the galaxy, 300 million years isn't really an obstacle at all. It's a comparatively small fraction of the available time, meaning that if even one civilization, anywhere, at any point in galactic history, had built and launched a single set of self-replicating probes, the entire galaxy, including our own solar system, should already be full of them. Tipler's conclusion was blunt. Because we don't see any von Neumann probes anywhere in our solar system, because nothing of the kind has ever turned up on the Moon, on Mars, in the asteroid belt, or anywhere else we've been able to look closely, he argued that this absence itself is strong evidence that no technological civilization capable of building them has ever arisen anywhere in the Milky Way, ever, across its entire history. This idea eventually became known as the Hart-Tipler conjecture, named jointly for Tipler and for physicist Michael Hart, who had made a related argument back in 1975, pointing out that the absence of extraterrestrials physically present on Earth itself was already a puzzle worth explaining. Carl Sagan, along with physicist William Newman, pushed back hard against Tipler's reasoning, arguing that it rested on too many unproven assumptions about the reliability, motivations, and unchecked growth of hypothetical machines, a disagreement that became known in the literature as the Sagan-Tipler debate. Their objection points to something real. A self-replicating system, whether biological or mechanical, doesn't necessarily expand forever without limit. It can run into resource shortages, replication errors that compound over generations the way genetic mutations do in biology, or simply a decision made by whatever intelligence built the first probe to stop expanding once a certain goal has been reached. Some more recent researchers studying the problem have proposed that self-replicating machines might even need something like a biological safeguard, a built-in limit on how many times they're allowed to copy themselves, similar to the way human cells contain a natural limit on cell division called the Hayflick limit, specifically to prevent a runaway, uncontrolled expansion that consumes everything in its path, sometimes described in the literature, half-jokingly, as the grey goo problem. Whichever side of that debate turns out to be right, the underlying math is what makes it worth mentioning at all. Unlike a radio signal, which requires someone to be listening at exactly the right frequency, at exactly the right moment, a self-replicating probe left behind on an asteroid or a moon would just sit there, silently, for as long as it takes anyone to eventually go looking, and nobody so far has found one. There's one more variation on the self-replicating probe idea worth mentioning, and it takes the whole concept somewhere considerably darker. It's called the Berserker hypothesis, named after a series of science fiction novels written by Fred Saberhagen beginning in 1963, which imagined a galaxy patrolled by self-replicating machines built for a single purpose: hunting down and destroying any civilization that shows signs of becoming a threat. As a proposed answer to the Fermi Paradox, the idea works like this. Instead of assuming self-replicating von Neumann probes simply explore and report back, this version imagines that such probes, once launched by some ancient civilization somewhere in the galaxy's deep past, either malfunctioned, were deliberately weaponized, or were built from the start to act as a permanent, automated defense system, one that identifies emerging technological civilizations, usually by detecting their radio signals, and systematically eliminates them before they can grow into competitors or threats. If something like that has been quietly patrolling the galaxy for hundreds of millions or even billions of years, it would neatly explain the silence. Civilizations don't get a chance to become loud, because the moment they start broadcasting, they get erased. The idea has attracted real scientific attention, not just science fiction interest. In 1983, science fiction author and physicist David Brin proposed, largely as a thought experiment, that the pattern of repeated mass extinction events in Earth's own fossil record and the unusually long gaps of time between them could theoretically be explained by exactly this kind of mechanism playing out on geological timescales. In 2013, researchers Anders Sandberg and Stuart Armstrong at Oxford's Future of Humanity Institute took the hypothesis seriously enough to run an actual game theory analysis of it, published under the title Hunters in the Dark, modeling how such deadly probes might behave and whether their existence is consistent with what we actually observe. Their conclusion offered a strange kind of comfort. Given how vast the galaxy is and how much time has passed, they argued that if berserker-style probes really existed and were actively hunting, even at a fairly slow rate of replication, they would almost certainly have already found and destroyed us, meaning the fact that we're still here broadcasting radio signals into space, mostly unbothered, is itself decent evidence against the hypothesis being true, at least in its most aggressive form. The berserker hypothesis also runs into the same basic problem that undermines a lot of these grim, hidden hunter explanations for the silence. If a network of hunter-killer machines has become powerful and widespread enough to systematically wipe out every emerging civilization across the galaxy, it should, in the process, be doing something detectable, dismantling planets, harvesting stars, or simply moving between star systems at the kind of speed and scale required to enforce a galaxy-wide quarantine, would likely leave behind exactly the kind of unusual energy signatures astronomers have been specifically looking for, and, so far, have not found. It's a genuinely unsettling idea to sit with, precisely because it can't be fully ruled out, but like nearly every other proposed solution to the Fermi Paradox, it ultimately runs into the exact same wall all the others do. There simply isn't enough evidence, in either direction, to say for certain whether it explains anything at all. Robin Hanson's warning about fearing the great filter in our future isn't just an abstract thought experiment, and it's worth grounding it in something concrete before moving on, because humanity has already come close enough to its own destruction that the danger isn't purely theoretical. On the night of September 26, 1983, a Soviet lieutenant colonel named Stanislav Petrov was on duty at Serpukhov 15, a secret command center outside Moscow, responsible for monitoring the Soviet Union's early warning satellite system for signs of an American nuclear first strike. Just after midnight, the system's alarms went off, and a screen lit up in red letters reading "Launch," reporting that a single American intercontinental ballistic missile had been fired at the Soviet Union. Within minutes, the system reported 4 more missiles behind it, and the computer's assessment of its own reliability read out at the highest possible confidence level. Petrov later recalled sitting in stunned silence for about 15 seconds, trying to process what the screen in front of him was telling him. His job, according to protocol, was to immediately report the launch up the chain of command, a report that, given the extraordinary tension of the Cold War at that exact moment, only 3 weeks after the Soviet military had shot down a civilian airliner, Korean Airlines Flight 007, would very likely have triggered a retaliatory Soviet nuclear strike against the United States and its NATO allies. Petrov didn't send the report. He reasoned that a genuine American first strike would almost certainly involve far more than 5 missiles, since a small, partial attack made little strategic sense, and he noted that ground-based radar stations, which scan for missiles as they rise above the horizon, were showing no corroborating evidence of anything in the sky at all. He made the decision, against direct military protocol, to classify the warning as a false alarm and wait for further confirmation rather than escalate it immediately. He was right. Investigators later traced the false alarm to a Soviet satellite called Cosmos 1382, which had mistaken sunlight reflecting off the tops of high-altitude clouds for the heat signature of missile launches. A Stanford professor studying the incident afterward estimated that a full-scale nuclear exchange triggered by that false alarm could have killed roughly 100 million people on its first day alone, with a death toll potentially reaching 1 billion within months as the broader consequences of a global nuclear war unfolded. One man's 15 seconds of hesitation is, by that estimate, the difference between the world we're living in right now and a version of Earth's history that could have ended civilization as we know it. This kind of near miss is exactly the sort of event the Great Filter Framework asks us to take seriously as a candidate for what might be lying ahead of us, rather than behind us. If technological civilizations across the galaxy reliably develop the capacity for self-destruction, whether through nuclear weapons, engineered pathogens, poorly governed artificial intelligence, or some other technology none of us have invented yet, at roughly the same stage of development where they also become capable of broadcasting detectable radio signals into space, then the Fermi Paradox's silence stops looking like evidence that intelligent life is rare. It starts looking like evidence that intelligent life reliably runs into a wall almost immediately after it becomes visible enough for anyone else to notice. A window so narrow that the odds of 2 civilizations existing in that same brief, dangerous stretch of time at the same moment, close enough to actually hear each other, could be vanishingly small, even if the galaxy is otherwise full of life. Nobody knows whether that's actually the pattern the universe follows, and there's no way to test it directly from a sample size of exactly one surviving civilization. But the fact that humanity's own history already includes at least one documented night when a single officer's 15 seconds of careful judgment stood between the modern world and something close to catastrophe is a sober reminder that the question Hansen posed in 1996, whether the filter lies behind us or ahead of us, isn't purely academic. It's a question with a body count already attached to how close we've come to answering it the hard way. Not every proposed answer to the Fermi Paradox assumes that nobody is out there. Some of the most interesting ones start from the opposite assumption, that intelligent civilizations might actually be common, and that the silence we experience is a choice being made on the other end, not an accident of cosmic rarity. The best-known version of this idea came from radio astronomer John A. Ball, who worked at the Harvard-Smithsonian Center for Astrophysics and published a short paper in the journal Icarus in 1973, titled simply The Zoo Hypothesis. Ball's argument was direct. He wrote that extraterrestrial intelligent life may be almost everywhere, and that the apparent failure of any of it to interact with us can be explained by the idea that advanced civilizations have deliberately set Earth aside, the same way a wildlife sanctuary or a nature reserve is set aside here on our own planet, specifically to allow a developing species to evolve on its own terms, without outside interference. In later writing, Ball speculated that extraterrestrial intelligence might be watching quietly and with real scientific interest, without ever intervening, reasoning that a planet's entire biosystem and culture would be worth studying by at least a few outside observers, even if direct contact was deliberately avoided. The zoo hypothesis has stuck around in the scientific literature for over 50 years now, and researchers studying the Fermi Paradox have noted that it's actually been cited more often in the past decade than it was during the first 35 years after it was published. Some scientists have proposed variations on the same basic idea. Researcher Jean-Pierre Rospars, speaking at a workshop on messaging extraterrestrial intelligence, suggested that any advanced civilizations nearby might be enforcing something like a galactic quarantine, on the theory that learning about a more advanced species prematurely could be genuinely disruptive to a younger civilization's own cultural and scientific development. Science fiction author and physicist David Brin proposed a closely related idea in 1983, sometimes called the nursery hypothesis, framing the silence less as a formal zoo and more as young civilizations being given space to grow up without interference, the interstellar equivalent of a parent stepping back to let a child learn to walk. There are real problems with the zoo hypothesis, and researchers who study it are generally upfront about them. The most obvious weakness is that it requires every single civilization out there, across the entire galaxy, spanning potentially enormous differences in culture, biology, and history, to agree on the same policy of silence and then actually stick to it without exception, indefinitely. Even one rogue civilization, or one accident, or one probe malfunctioning would be enough to break the pattern, and researchers analyzing the idea have pointed out that this makes the hypothesis vulnerable in a way that a purely physical explanation, like a great filter, isn't. There's also a deeper philosophical objection. Critics argue that the zoo hypothesis quietly assumes humanity is important enough to be worth hiding from in the first place, a kind of unearned self-importance that runs directly against the Copernican principle, the same scientific instinct that says Earth shouldn't be assumed to be special or central to anything. If nobody out there actually cares enough about us to bother hiding, the whole idea falls apart on its own. Even so, some researchers have taken the zoo hypothesis seriously enough to propose actually testing it directly, arguing that if an advanced civilization truly is watching and waiting for the right moment, a clear, deliberate, and unmistakably intelligent signal sent from Earth, inviting a response, might be the one thing capable of finally breaking that silence. There's one final idea worth including, not because it directly answers the Fermi Paradox, but because it emerges from a strikingly similar way of reasoning about civilizations, probability, and scale, and it's become impossible to talk about questions like this one without someone eventually bringing it up. In April of 2003, Swedish philosopher Nick Bostrom, then working at the University of Oxford, published a 13-page paper in the academic journal Philosophical Quarterly titled, "Are You Living in a Computer Simulation?" Bostrom's argument doesn't actually claim, despite how it's usually summarized in casual conversation, to prove that we are living inside a simulation. What it actually proves is a trilemma, a set of three possible statements, where, according to Bostrom's reasoning, at least one of the three has to be true, even though we currently have no way of knowing which one. The first possibility is that the human species, or any comparable technological species anywhere, is very likely to go extinct before ever reaching what Bostrom calls a post-human stage, meaning a level of technological development advanced enough to run large numbers of highly detailed simulations of entire civilizations and conscious minds. The second possibility is that civilizations do reach that post-human stage, but for whatever reason, whether ethical objections, lack of interest, or some other consideration, they choose not to run large numbers of simulations of their own ancestral history. And the third possibility, the one that tends to get all the attention, is that if neither of the first two statements is true, meaning civilizations do commonly survive to a post-human stage, and they do commonly choose to run enormous numbers of simulations, then the number of simulated conscious minds experiencing something like human history would vastly outnumber the number of minds experiencing the single, original, non-simulated version of that history. Assuming there's no way to tell from the inside which category you belong to, the argument concludes that a randomly selected conscious observer, which includes you, would almost certainly find themselves in one of the simulated versions rather than the original. Bostrom himself has generally been careful to describe his own confidence across the three possibilities as roughly split into thirds, rather than fully endorsing the simulation conclusion outright, and the argument has drawn substantial criticism and refinement in the more than 2 decades since it was first published, including philosophical objections to the specific probability reasoning it relies on, and questions about whether consciousness could actually be replicated inside a simulated system in the first place. What makes it worth mentioning here, connected to everything else in this video, is the structural resemblance it bears to the Fermi Paradox and the Great Filter. All three arguments start from the same basic move, taking an assumption about how common or how capable advanced civilizations are likely to be, and following that assumption to its logical extreme to see what it implies about our own specific situation. The Fermi Paradox asks what it would mean if advanced civilizations were common, and yet we see none of them. The Great Filter asks what it would mean about our own future if we take that silence completely seriously, rather than explaining it away. And Bostrom's simulation argument asks what it would mean about the nature of our own reality if advanced civilizations, ours or any other, commonly survive long enough to develop computing power vastly beyond anything humanity has ever built. None of these arguments can currently be tested in any direct way, and none of them offer a comfortable, settled answer. What they share, more than anything else, is a willingness to take an uncomfortable hypothetical completely seriously and follow it all the way to wherever the math actually leads, rather than stopping halfway simply because the conclusion turns out to be strange. While most of the search for extraterrestrial intelligence has involved listening, humanity has also, on a handful of occasions, tried actually speaking first. The most famous of those attempts happened on November 16, 1974, when scientists at the Arecibo Observatory in Puerto Rico used the massive radio telescope, designed in part by Frank Drake himself, to broadcast a single message toward the globular star cluster M13, a dense cluster of stars roughly 25,000 light-years away. The transmission was built in binary code and, once decoded, formed a crude image containing the numbers 1 through 10, the atomic numbers of the elements that make up DNA, a graphic representation of the double helix itself, a simple figure of a human being alongside the population of Earth at the time, a sketch of our solar system, and an image of the Arecibo telescope that sent the whole thing. The message was never meant as a genuine attempt to start a conversation. It was broadcast only once, during a ceremony celebrating a renovation of the telescope, and was intended more as a demonstration of what human technology could do than a serious effort to be understood. Given that it will take roughly 25,000 years just to arrive, and another 25,000 years for any reply to make its way back, Nobody involved in sending it ever expected to hear back in their own lifetime, or in the lifetime of their species as we currently know it. 3 years later came a more ambitious and much more personal effort. In the late summer of 1977, NASA launched 2 spacecraft, Voyager 1 and Voyager 2, on a mission to study the outer planets of our solar system. Voyager 2 actually launched first on August 20, 1977, followed by Voyager 1 on September 5th, because both spacecraft were destined to eventually leave the solar system entirely and drift through interstellar space indefinitely. NASA authorized the inclusion of something extra on each one, a gold-plated copper phonograph record housed in a protective aluminum jacket, now known as the Voyager Golden Record. A committee led by Carl Sagan spent months assembling its contents, and what they built amounts to a genuine, thoughtful attempt at a self-portrait of the entire species. The record contains spoken greetings in 55 different languages, along with a range of natural and human sounds, laughter, animal calls, weather, and music. It also carries 116 images encoded onto the record, including diagrams, mathematical concepts, and photographs, some pulled from the United Nations Photo Library. The record itself was engraved with a set of instructions, using pictograms and physics, showing exactly how to play it and how to reconstruct the images from the data. Both Voyager spacecraft have since gone further than any human-made object in history. Voyager 1 became the first human-built craft to enter interstellar space in 2012, with Voyager 2 following in 2018, meaning both golden records are now drifting silently beyond the edge of our sun's direct influence, carrying a snapshot of who we were in 1977 into a void that operates on timescales that make human history look instantaneous. Neither Voyager probe is aimed at any particular star, so the record isn't a message with a target the way the Arecibo broadcast was. It is, more than anything else, a kind of message in a bottle, tossed into an ocean so vast that the odds of it ever washing up on any shore are close to impossible to calculate, and yet the people who built it decided the attempt was worth making anyway. Not everyone has agreed that attempts like these are a good idea. This broader practice, deliberately transmitting messages toward other stars in the hope of being noticed, is known as active SETI, or sometimes METI, short for Messaging Extraterrestrial Intelligence, and it has been a genuine point of tension within the scientific community for decades. The physicist Stephen Hawking was among those who publicly warned that deliberately advertising our location and technological capability to unknown civilizations could be dangerous, reasoning that any species capable of crossing interstellar distances to find us might not have friendly intentions, in much the same way that contact between technologically mismatched civilizations throughout human history has rarely gone well for the less advanced side. Others in the field, including some of the researchers behind the Arecibo message and the Golden Record, have argued the opposite, that a civilization advanced enough to actually reach us would have no practical need for anything we have, and that the entire fear rests on projecting distinctly human, distinctly earthly motives, like conquest and resource scarcity, onto a species we know nothing about. That disagreement has never been resolved, and it remains one of the more genuinely unsettled ethical questions tied up in the search for intelligent life, a question about whether reaching out into a silent galaxy is an act of hope or a risk nobody has the authority to take on behalf of the entire planet. The tools available today would have seemed like science fiction to the 12 people sitting in that room at Green Bank in 1961. The James Webb Space Telescope, along with ground and space-based spectroscopy programs tracked through the NASA Exoplanet Archive, is now capable of analyzing the atmospheres of some exoplanets directly, breaking down starlight that passes through a planet's air to look for chemical signatures, sometimes called biosignatures, that might indicate biological activity. The archive's own weekly update logs show just how routine these discoveries have become. In one recent update alone, a team using data from NASA's Transiting Exoplanet Survey satellite confirmed 114 new planets in a single announcement, described by the archive as the largest mass confirmation of test planets to date. Another update highlighted a planet roughly Earth size, found hiding in old, archived Kepler and K2 data, sitting near the outer edge of the habitable zone, around a star about 70% the size of our Sun. located 146 light-years from Earth. NASA also launched a new mission called Pandora in January of 2026, designed specifically to study the atmospheres and host stars of exoplanets in more detail, adding yet another set of eyes to a search that keeps expanding year after year. Meanwhile, the Breakthrough Listen initiative continues to sweep the sky for radio and optical signals, including repeated modern searches aimed specifically at that same patch of sky near Sagittarius, where the WOW signal came from in 1977, still without finding anything that repeats it. All of that new data has actually done something interesting to the Fermi Paradox itself. It hasn't answered it, but it has sharpened exactly where the mystery lives. We now know, with real confidence, that planets are common. The old assumption that Earth-like worlds might simply be too rare to matter has been dismantled by the numbers. 6,000 confirmed exoplanets, and climbing toward what scientists expect to be 10,000 within just a few years. That means the uncertainty has been squeezed almost entirely into the back half of the Drake equation, the part nobody has ever been able to measure. It's not about whether planets exist anymore. It's entirely about whether life gets started on them, whether that life ever becomes intelligent, and whether intelligence, once it exists, manages to survive long enough to reach out and be noticed by anyone else. Nowhere has the tension between hope and rigorous caution played out more publicly in recent years than around a single exoplanet called K2 1Ceres b, a world roughly 8.6 times as massive as Earth, orbiting a cool dwarf star about 120 light-years away, sitting comfortably inside that star's habitable zone. In 2023, a team of astronomers using the James Webb Space Telescope detected methane and carbon dioxide in the planet's atmosphere, a combination consistent with what scientists call a Hycean world, a theoretical class of planet with a liquid water ocean sitting beneath a thick, hydrogen-rich atmosphere. That same 2023 analysis included a tentative, low-confidence hint of something else entirely, a gas called dimethyl sulfide, or DMS, which on Earth is produced almost exclusively by marine phytoplankton and other ocean-dwelling life. Then, in April of 2025, the same research team, based largely at Cambridge University, announced they'd found the signal again, this time with new mid-infrared data, describing it as the strongest hint yet of biological activity found outside our solar system. Cambridge's own press office promoted the finding aggressively, and headlines around the world followed. The scientific response was immediate, and it was not uniformly enthusiastic. Other researchers began independently reanalyzing the exact same US data almost right away. Astrophysicist Jake Taylor at the University of Oxford posted a preliminary study just days after the announcement, finding no strong statistical evidence for dimethyl sulfide, or its close chemical cousin, dimethyl disulfide, in the same dataset at all. Later, a more detailed reanalysis, published through NASA in the summer of 2025, confirmed that K2-18b does appear to be genuinely water-rich with a complex atmosphere, but it found no conclusive evidence supporting the original DMS detection, and it specifically flagged the difficulty of separating a real astrophysical signal from what researchers call red noise, essentially statistical static in the instrument data that can masquerade as a genuine signal if you're not careful. A separate paper published later in 2025 went further, arguing directly that the K2-18b data simply does not meet what astrobiologists call the standards of evidence for a claim of extraterrestrial life, concluding that the apparent large features seen in the mid-infrared spectrum were in tension with the smaller, more reliable features seen in the near-infrared data, and that no statistically significant biosignature evidence currently exists for this planet. Other groups have continued to defend a version of the detection at a modest confidence level, generally described as 3 sigma significance, which in ordinary terms means there's still a real chance, roughly 1 in a few hundred, that what looks like a signal is actually just noise. If this entire back and forth sounds familiar, that's because it closely mirrors an earlier, very similar controversy involving the planet Venus, where scientists in 2020 claimed to have detected phosphine gas, another potential biosignature, in its atmosphere, only for that claim to be challenged almost immediately and to remain unresolved and disputed years later. What both cases illustrate, more than anything else, is exactly how difficult this kind of detection actually is, and how easily a genuinely exciting result can outrun the evidence supporting it once it reaches the public. The scientists working directly on K2-18b have generally been far more careful in their own technical papers than the headlines describing their work, consistently describing the DMS signal as tentative, low confidence, or requiring follow-up, even as public coverage frequently dropped those qualifiers entirely. K2-118b isn't the only nearby system drawing this kind of intense scrutiny. Roughly 40 light-years away sits TRAPPIST-1, a small, cool, ultra-dim star, first found to host multiple transiting planets through ground-based observation and later studied extensively using NASA's Kepler and K2 missions. TRAPPIST-1 turned out to host 7 planets, all comparable in size to Earth, locked together in an unusually precise chain of orbital resonances, meaning their orbital periods relate to one another through simple whole number ratios, a pattern researchers have described as a complex, interlocking rhythm linking every single planet in the system to its neighbors. Several of those 7 worlds sit within or near the system's habitable zone, and TRAPPIST-1 has become one of the most closely studied planetary systems in the search for potentially habitable, Earth-sized worlds outside our own solar system, specifically because it offers so many candidates clustered so closely together around a single, nearby star. Between K2-118b and TRAPPIST-1, and the hundreds of other candidate worlds now sitting in astronomers' queues waiting for just observing time, it's clear that the next real breakthrough in this search, if and when it comes, likely won't arrive as a single dramatic signal picked up on a radio telescope. It will probably look exactly like this: a faint chemical signature buried in noisy data, argued over carefully by dozens of scientists for years, before anyone is confident enough to actually call it what everyone hopes it might be. Before leaving TRAPPIST-1 behind, it's worth being honest about a serious complication that recent research has uncovered, because it tempers a lot of the early excitement about that system specifically, and it applies to a huge share of the potentially habitable worlds discovered anywhere in the galaxy. TRAPPIST-1 is what astronomers call a red dwarf, or an M-dwarf, a small, cool, dim star with only about 8% of our own Sun's mass. Red dwarfs happen to be, by a wide margin, the most common type of star in the entire Milky Way, which is exactly why systems like TRAPPIST-1 have generated so much excitement in the first place. If planets around stars like this can actually support life, it would mean potentially habitable worlds are far more common across the galaxy than previously assumed. But red dwarfs come with a serious catch. Despite being smaller and cooler than the Sun, they tend to be significantly more magnetically active, producing frequent, powerful flares of ultraviolet and X-ray radiation, along with intense bursts of charged particles, far more often than a calmer, more sedate star, like our own Sun does. Because a red dwarf's habitable zone sits so much closer to the star itself, any planet orbiting inside that zone, close enough for liquid water to potentially exist, is also sitting close enough to take a direct hit from every one of those flares. Recent observations have shown exactly how damaging that proximity can be. Research published in 2024 found direct evidence that TRAPPIST-1e, one of the system's most promising potentially habitable planets, is actively having its atmosphere stripped away, driven by electric currents generated as the planet races through the stellar wind streaming off its host star at extremely close range. One of the researchers involved in that study put it bluntly, saying that they'd expect every single planet in the TRAPPIST-1 system to have a genuinely difficult time holding on to any atmosphere at all under those conditions. TRAPPIST-1b, the innermost of the system's 7 planets, appears to have already lost its atmosphere entirely. Further observations using the James Webb Space Telescope, looking specifically at TRAPPIST-1b and TRAPPIST-1c, the 2 innermost worlds, found no detectable signs of any atmosphere on either planet whatsoever, though those 2 specific worlds sit outside the habitable zone and were never considered strong candidates for life to begin with. The question of whether the more promising, farther-out planets, TRAPPIST-1e, F, and G, have managed to hold on to meaningful atmospheres despite the star's activity remains genuinely open, and is one of the specific questions astronomers are actively using JEST to try to answer right now. There's an added complication layered on top of the radiation problem. Because red dwarf habitable zones sit so close to their star, planets orbiting inside them are almost certainly tidally locked, meaning the same side of the planet permanently faces the star, exactly the way the same side of our moon always faces Earth. That produces a world with one hemisphere trapped in permanent blazing daylight and the other locked in permanent darkness, an arrangement that creates enormous challenges for maintaining any kind of stable, life-friendly climate. Though some researchers have proposed that a sufficiently thick atmosphere, if a planet manages to hold on to one at all, could potentially circulate enough heat between the two hemispheres to keep a habitable band alive somewhere near the twilight boundary between day and night. None of this rules out life around red dwarf stars entirely, and scientists remain genuinely motivated to keep looking, precisely because these stars are so overwhelmingly common that even a modest fraction of habitable planets around them would still represent an enormous number of potentially life-bearing worlds across the galaxy. But it's a meaningful complication to the Eta-Earth estimates covered earlier in this video, because those estimates were built primarily around Sun-like stars, and it's a real reminder that finding a planet in the right temperature zone is only the first of several hurdles a world has to clear before it has any real chance of supporting the kind of long, stable, billions of years history that produced intelligent life here on Earth. The search for a signal, in the meantime, has never been better funded or more technologically capable than it is right now. In July of 2015, at a gathering held at the Royal Society in London, Russian entrepreneur Yuri Milner stood alongside physicist Stephen Hawking and a group of prominent scientists, including Frank Drake himself, then in his 80s, to announce a new program called Breakthrough Listen. Milner committed $100 million of his own funding to the project over 10 years, describing it at the time as an effort to bring what he called a Silicon Valley approach to the search for intelligent life in the universe. Hawking, serving in an advisory role, said simply that he strongly supported the initiative and the broader search for extraterrestrial life, and Drake, whose own equation had launched the modern search 54 years earlier, told the crowd that right now, at this very moment, there could be messages from the stars flying directly through the room, through everyone standing in it, adding that the thought still, in his words, sends a shiver down his spine. Breakthrough Listen secured significant dedicated observing time on two of the most powerful radio telescopes on the planet, the 100-meter Green Bank Telescope in West Virginia, the same observatory where Drake had chalked his equation onto a blackboard back in 1961, and the 64-meter Parkes Telescope in New South Wales, Australia. The project set out to survey more than 1 million of the nearest stars, the plane and center of the Milky Way, and the 100 nearest galaxies beyond our own, looking for both radio signals and laser pulses, all while making every byte of collected data freely available to the public, constituting what organizers described as likely the largest single release of scientific data ever made openly accessible to anyone in the world. It's worth pausing on just how sensitive this kind of search has become, because the numbers put the scale of the challenge into real perspective. According to figures released with the Breakthrough Listen announcement, the project's telescopes are sensitive enough that if a civilization based around any of the 1,000 nearest stars to Earth were transmitting with nothing more powerful than an ordinary aircraft radar, the array could detect it. Its optical search, scanning for laser pulses rather than radio waves, is sensitive enough that it could, in principle, detect something as faint as a single 100-watt household light bulb, if that light bulb happened to be located on a planet 25 trillion miles away and pointed directly at Earth. That is an extraordinary technical achievement, and it's also a humbling illustration of exactly how faint and how deliberately targeted a signal would have to be for us to catch it at all, even with the best instruments humanity has ever built, pointed at exactly the right patch of sky at exactly the right moment. While Breakthrough Listen keeps its ears turned outward toward other stars, a separate and quieter branch of the search has been turning its attention inward, toward a handful of frozen moons orbiting the outer planets of our own solar system. Jupiter's moon Europa and Saturn's moon Enceladus have both emerged as leading candidates in the hunt for life closer to home. Not because their icy, sunless surfaces look inviting, but because of what scientists believe is hidden underneath. Data from NASA's earlier Galileo mission and from the Cassini spacecraft, which directly sampled material erupting from geysers near Enceladus's south pole, strongly suggest that both moons conceal vast liquid water oceans beneath their frozen shells. Oceans that may have existed in Europa's case for as long as 4.5 billion years, potentially longer than Earth's own oceans have existed. Scientists believe both moons' rocky seafloors are likely in direct contact with those oceans, which raises the possibility of hydrothermal vents similar to the ones found deep in Earth's own Pacific Ocean, first discovered along a stretch of seafloor called the Galapagos Rift, where entire ecosystems of complex organisms thrive in permanent darkness, powered not by sunlight, but by chemical energy rising directly out of the planet's own interior. NASA launched the Europa Clipper mission on October 14, 2024, carrying the largest solar panels ever built for a NASA planetary spacecraft, spanning some 30 meters across, along with a suite of instruments designed to map Europa's composition and search directly for organic molecules and other potential chemical signatures of life, in what scientists have described as an astrobiology mission by stealth, one that could, in the most fortunate possible scenario, detect actual evidence of life during its flybys of the icy moon. None of this would answer the Fermi Paradox on its own, even in the best case. Finding microbial life thriving in the dark ocean beneath Europa's ice would be one of the most important scientific discoveries in human history, but it wouldn't put a radio dish or a spacecraft in our sky. It would, however, answer half of the oldest question in this entire field, the half asking whether life itself is rare, while leaving the far harder half, whether intelligence is rare too, exactly as open as it's always been. The WOW signal, it turns out, has actually had a major update since 1977, and it happened quite recently. In 2024, a research team led by Abel Mendez at the Planetary Habitability Laboratory published a paper titled Arecibo WOW, proposing the first genuinely serious natural explanation for the signal in decades. Mendez and his colleagues had been sifting through archival data from an entirely different Arecibo survey, one studying radio emissions from red dwarf stars, when they noticed something that stopped them: cold, faint, narrowband signals emerging from clouds of cold, neutral hydrogen scattered across the galaxy, signals that looked structurally similar to the WOW signal itself, just far weaker. Mendez has since described the moment of recognition directly, saying that he immediately connected it to the older mystery. The team's hypothesis is that the original 1977 signal may have been triggered by a rare astrophysical event, an intense, short-lived burst of radiation, possibly from a magnetar, an extraordinarily dense, highly magnetized neutron star, or from something called a soft gamma repeater, striking a cold interstellar hydrogen cloud and causing a sudden, brief brightening of that cloud's natural hydrogen emission, in a process similar to how a laser works, called a maser. In 2025, the same team published a follow-up study, Arecibo WOW, going back through the original archival Ohio SETI data using modern analysis techniques and revising several of the signal's core properties, including a peak flux density measured at roughly 4 times the previously accepted strength and a slightly adjusted position and frequency compared to the widely cited original measurements from the 1970s. It's worth being precise about what this new research does and doesn't claim, because press coverage has occasionally overstated it. One of the study's own co-authors, astrophysics graduate student Kevin Ortiz Ceballos, described the magnetar and hydrogen cloud explanation directly as, in his own words, definitely a bit speculative, adding that the team wasn't claiming certainty, only that they'd identified what they considered a genuinely exciting and physically plausible hypothesis worth taking seriously. It also isn't the first attempt at a mundane explanation. Back in 2016, astronomer Antonio Paris proposed that a passing comet might have produced the signal, an idea that was directly and specifically refuted within days by Jerry Eman and the original Ohio SETI team themselves, who pointed out that a comet would have produced a broad, diffuse signal spread across a wide area of sky rather than the sharp, cleanly bounded signal Big Ear actually recorded. A separate proposal in 2020 pointed toward a specific sun-like star roughly 1,800 light-years away as a possible origin point. None of these explanations, including the newest magnetar and hydrogen cloud hypothesis, have been confirmed, and none have achieved anything close to scientific consensus. What has changed is the balance of the conversation. For nearly 50 years, the WOW signal existed in a kind of scientific limbo, too strange and too well documented to dismiss outright, but with no plausible natural mechanism ever proposed that actually fit its specific properties. The 2024 and 2025 research is the first serious attempt to close that gap with real, physically grounded astrophysics rather than speculation. And whether or not the magnetar hypothesis eventually holds up under further scrutiny, it represents exactly the kind of careful, iterative, self-correcting process that defines how real progress gets made on questions like this. The same process now playing out in real time over the K2-118b biosignature claim, and the same process that, sooner or later, will have to settle the question of what actually happened over Ohio on that August night in 1977, one way or the other. There's one more idea worth sitting with before pulling all of this together, and it comes from Jill Tarter, the astronomer who co-founded the SETI Institute and spent her entire career leading the modern search for extraterrestrial intelligence. Tarter has pushed back for decades against the assumption, often baked quietly into the Fermi Paradox itself, that humanity has actually looked hard enough to draw any real conclusions from the silence at all. Along with her collaborators, she's compared the entire history of Radio SETI to dipping a single drinking glass into Earth's oceans and, finding no fish in that one glass, concluding that the oceans must be empty. A 2018 study, published under the title How Much SETI Has Been Done, Finding Needles in the N-Dimensional Cosmic Haystack, took that metaphor and turned it into an actual quantitative model, treating the search for alien signals as a search through an 8-dimensional haystack, one that accounts not just for which stars we've pointed telescopes at, but for the specific radio frequencies scanned, the sensitivity of the equipment used, how long each observation lasted, and how much of the sky was covered during each search. When researchers actually ran the math, accounting for every SETI program conducted up to that point, the answer was almost comically small. Humanity, according to that analysis, has meaningfully searched only an infinitesimal fraction of the full haystack where a genuine signal could be hiding, a number so far below 1% that describing 70 years of searching as inconclusive starts to feel like an understatement rather than an overstatement. That reframing matters, because it cuts directly against one of the more common casual dismissals of the entire search, the argument that if intelligent life were really out there, surely we'd have picked up a signal by now. Tarter, when pressed by interviewers to give her own personal best guess about whether intelligent life exists elsewhere in the universe, has consistently declined to answer, explaining that offering a guess without real evidence behind it would amount to stating a belief rather than a scientific conclusion, and that her entire career has been built around trying to convert that verb, to believe, into a different verb entirely, to explore. Jason Wright, a SETI researcher at Penn State University, who has written extensively on the current state of the field, has made a related point, describing the Fermi Paradox and the Drake equation as genuinely foundational to the field's history, while also cautioning that decades of purely theoretical debate about the paradox, without new data to test any of it against, risks running into steeply diminishing returns until an actual detection, or a definitive non-detection covering a truly comprehensive search, finally gives researchers something solid to reason from. Drake himself, reflecting on his own equation decades after writing it, offered a description that other researchers in the field have echoed ever since, calling it not a tool for producing a confident answer, but, in his words, a wonderful way to organize our ignorance. Every framework covered in this video, the Great Filter, the Rare Earth Hypothesis, the Zoo Hypothesis, the Berserker Hypothesis, the Kardashev Scale, is, in the end, exactly that, a structured, careful way of organizing what we genuinely don't know, while the actual searching, the radio dishes, the spectrometers, the spacecraft headed toward icy moons, keeps quietly, patiently continuing in the background, waiting for the moment that ignorance finally gets organized into something else entirely. The 2023 and 2024 congressional hearings didn't emerge out of nowhere. They're the latest chapter in a story that stretches back nearly 80 years, to the summer of 1947, when pilot Kenneth Arnold reported seeing 9 strange objects flying in formation near Mount Rainier in Washington state. moving at what he estimated was nearly 1,900 kilometers per hour, a speed that seemed almost impossible for anything built at the time. Arnold described their motion as looking like a saucer skipping across water, and when the story hit the press, the phrase "flying saucer" entered the American vocabulary almost overnight. Barely a month later, in July of 1947, a ranch foreman named W. Brazel discovered strange debris scattered across a property in Lincoln County, New Mexico, not far from Roswell. The local Army Airfield's Public Information Office issued a press release stating that the military had recovered a flying disc, a statement that made headlines around the world for exactly 1 day before a second press release walked it back entirely, describing the debris as nothing more than a weather balloon. That reversal, rather than settling the matter, planted a seed of suspicion that has never fully gone away. It would take until the 1990s for the Air Force to offer a fuller explanation, revealing that the debris actually came from a classified program called Project Mogul, a set of high-altitude balloons designed to listen for the acoustic signature of Soviet atomic bomb tests, a program secret enough at the time that military officials chose to let the public believe in a weather balloon rather than reveal what the equipment was actually for. The Roswell incident set the pattern for nearly everything that followed. In 1948, the U.S. Air Force launched Project Sign, its first formal investigation into UFO reports, which was renamed Project Grudge the following year, and then reorganized again in 1952 into the program most people now recognize by name, Project Blue Book. Operating out of Wright-Patterson Air Force Base in Dayton, Ohio, Project Blue Book ran for 17 years, from 1952 until 1969, and over that time investigated more than 12,000 separate UFO reports. When the program finally closed, the Air Force reported that the vast majority of those cases had been explained as misidentified aircraft, weather phenomena, astronomical objects, or hoaxes, but a small residual fraction, roughly 6% by some counts, several hundred individual cases, were closed as officially unexplained, neither confirmed as anything extraordinary nor conclusively resolved as anything mundane. That unresolved residue is, in a real sense, the direct ancestor of everything that came later. The 2007 launch of a classified Pentagon program studying the issue, the formation of the Unidentified Aerial Phenomena Task Force in 2020, its replacement in 2022 by the All-Domain Anomaly Resolution Office, and eventually the public testimony delivered under oath in 2023 and again in 2024. Across nearly 80 years and several different generations of government investigators, the basic shape of the story has stayed remarkably consistent. A small number of reported cases that resist easy explanation, an official government posture that alternates between public reassurance and periods of genuine, documented secrecy, and a public that has, across decades of polling, remained persistently split between skepticism and the suspicion that something real is being withheld. Everything covered so far comes from the world of mainstream astrophysics and astrobiology. Professional scientists working with telescopes, spectrometers, and peer-reviewed data. There's a separate, much more politically charged thread running alongside all of this, centered not on distant exoplanets, but on unidentified objects, reported much closer to home, and it's worth covering honestly, including the parts that remain genuinely unresolved. In June of 2023, journalists Leslie Kean and Ralph Blumenthal published a report featuring claims from David Grush, a former intelligence officer who had served on the Pentagon's Unidentified Aerial Phenomena Task Force. Grush alleged that the United States government had been running a multi-decade program to recover and reverse-engineer crashed craft of what he described as non-human origin, and that the government had also recovered non-human biological material from crash sites. On July 26, 2023, Grush testified to those same claims under oath before a House Oversight Subcommittee, alongside former Navy pilots Ryan Graves and David Fravor, who separately described their own encounters with unidentified aerial objects during military operations and raised concerns about the potential safety risks these objects pose to military aircraft, regardless of what they actually turned out to be. The Pentagon's response was direct and consistent. A spokesperson for the Department of Defense's All-Domain Anomaly Resolution Office, or ARO, the office created in 2022 specifically to investigate these reports, stated at the time that it had found no verifiable information to substantiate claims that any program involving the possession or reverse engineering of extraterrestrial materials has ever existed. A second congressional hearing followed in November of 2024, featuring additional witnesses including a retired Navy Rear Admiral and Luis Elizondo, a former Pentagon official who had previously run a separate program studying unidentified phenomena before resigning in 2017. Elizondo described the situation to lawmakers as, in his words, an enigma and a frustration, adding that some of the technology described in these reports appeared to outperform anything currently in the American military's own inventory. In March of 2024, RO published the first volume of its own historical record report, covering government-related UAP claims from 1945 through October of 2023, and the office's acting director at the time summarized its conclusion plainly, stating that RO had found no verifiable evidence that any UAP sighting has ever represented genuine extraterrestrial activity. That gap between whistleblower testimony describing recovered non-human craft and biological material on one side, and an official government investigation reporting no verifiable evidence to support those same claims on the other, has never been closed, and it remains exactly that, a gap, rather than a settled question in either direction. It's a genuinely different kind of uncertainty than anything else in this video. The scientific search for extraterrestrial intelligence, the Drake equation, the wow signal, the Great Filter, the ongoing work with the James Webb Space Telescope, all of it operates through public, peer-reviewed data that any qualified scientist anywhere in the world can independently check and challenge, which is exactly the process that produced the back-and-forth scrutiny over the K218b biosignature claim. The UAP testimony operates almost entirely through classified programs, personal testimony, and government statements that can't be independently verified by outside researchers at all, which means it simply isn't possible, with the information currently available to the public, to say with any real confidence whether these claims describe a genuine and previously hidden discovery, a case of mistaken identity involving classified human aircraft, or something else entirely. What can be said with confidence is that the questions raised in these hearings pushed the US government toward more public disclosure on this topic than at almost any point since the 1960s, and that Congress, across two different sessions and under two different political administrations, judged the underlying claims serious enough to bring senior military and intelligence officials in to testify about them under oath, in public, on the record. So let's finally sit with the actual premise of this video, now that we've walked through the entire body of evidence, the theories, the controversies, and the honest uncertainty behind all of it, and take seriously what it would actually mean if humanity really is the only intelligent civilization the Milky Way has ever produced. It would mean every atom in your body, every idea anyone has ever had, every war and every symphony and every language exists nowhere else across roughly 400 billion star systems and at least 300 million confirmed Earth-sized worlds sitting in the habitable zones of sun-like stars alone. It would mean the closest thing the universe has to a witness to its own beauty, someone capable of pointing a telescope at a nebula and feeling something about it, someone capable of writing an equation on a chalkboard in 1961 or circling a strange signal in red ink in 1977, is us, and only us, scattered across a galaxy roughly 100,000 light-years wide. It would also mean that whatever obstacle stands between simple chemistry and a lasting, spacefaring civilization, whether that great filter sits behind us in our evolutionary past or somewhere ahead of us in our technological future, we are either the rare species that already cleared it, or we are the current test case still walking toward it, without any way of knowing exactly where the edge is. Neither possibility is fully comfortable, and it's worth walking through why, one more time, with everything we've now covered laid out on the table. If the filter sits behind us, somewhere in the improbable jump from lifeless chemistry to the first self-replicating cell, or in the billion-year climb from simple single cells to complex ones, or in the specific, unlikely combination of a stable star, a protective magnetic field, active plate tectonics, and a moon formed by exactly the right kind of ancient collision at exactly the right angle, then we are, statistically speaking, an extraordinary fluke. That version of the story carries its own strange weight. It would mean we may be functioning as the only lasting record the universe will ever produce of this particular kind of story, this particular species, this particular history, unless we make a deliberate choice to carry it further ourselves, whether that's through a golden record drifting silently past the edge of the solar system, or through something far more ambitious that hasn't been built yet. If the filter is still ahead of us instead, tucked somewhere in the transition from a technological civilization to a stable, long-lived, spacefaring one, then the silence coming from the rest of the galaxy stops being neutral information and starts looking like a warning sign, a pattern showing that civilizations at our stage of development tend not to make it much further before something, whether it's environmental collapse, resource exhaustion, unchecked and poorly governed technology, or simply catastrophic bad luck, brings the story to an end. As Robin Hanson wrote back in 1996, if the great filter can't be found in our past, it has to be feared in our future. And right now, with every telescope, every spectrometer, and every accumulated year of searching, nobody, not the most advanced observatory on Earth, and not the most careful scientist who has ever studied this question, can tell you for certain which version of the story we're actually living in. What makes this moment genuinely different from every other point in the 70-plus years since Fermi first asked his question is how much closer the tools have gotten to potentially answering it. We've walked through a lot of ground to get here, so it's worth recapping exactly how far the picture has shifted. In 1961, when Frank Drake wrote his equation on a chalkboard in Green Bank, not a single planet had ever been confirmed around another star, and every term in his formula, beyond the star formation rate itself, was pure, honest guesswork. Today, the NASA Exoplanet Archive lists more than 6,000 confirmed worlds, with researchers expecting that number to reach 10,000 within just a few years, and hard observational data now puts the number of Earth-sized planets sitting in the habitable zones of Sun-like stars, in our galaxy alone, at a conservative minimum of 300 million. The Kardashev Scale gives astronomers a concrete framework for what an advanced civilization's energy use should look like from a distance, and systematic searches for that exact signature, unusual infrared emission consistent with a Dyson sphere or a galaxy-spanning Type 3 civilization, have so far come back completely empty. The Great Filter remains the single most sobering framework anyone has proposed for understanding the silence, precisely because it refuses to offer false comfort in either direction. The rare Earth hypothesis, backed by real geological and astronomical evidence about Earth's magnetic field, its plate tectonics, and its unusually well-timed moon, suggests our own planet may sit far out on the lucky tail of a very unforgiving distribution. Von Neumann probes and the Hart-Tipler conjecture point out that even a single ancient civilization, anywhere in galactic history, should have already filled the Milky Way with self-replicating machines by now, and nobody has found one, not on the Moon, not on Mars, not anywhere in the asteroid belt. The zoo hypothesis and the berserker hypothesis sit at opposite emotional extremes of the same basic idea, that intelligent life might actually be common, and the silence is a choice, whether protective or predatory, being made by someone we simply haven't detected yet. Panspermia and the extraordinary resilience of extremophiles like tardigrades complicate the picture further, suggesting that once life gets a foothold anywhere, it might be far more transportable and far more durable than a strictly earthbound view of biology would ever have predicted. And closer to home, missions like Europa Clipper are actively investigating whether Earth's own solar system might already be quietly hosting a second, independent origin of life, in the dark, hidden ocean beneath the ice of a moon most people have never given a second thought to. Every single piece of that effort, from the Green Bank Conference in November of 1961, to Jerry Eman circling 6 letters and a number in red ink one August morning in 1977, to Yuri Milner and Stephen Hawking standing at the Royal Society in July of 2015, committing $100 million to listen more carefully than anyone ever had before, to a spacecraft carrying a 30-meter solar array launched toward Jupiter's icy moon in October of 2024, is really just an extension of the exact same question Enrico Fermi asked over lunch at Los Alamos in the summer of 1950. Where is everybody? 70+ years later, across more than 6,000 confirmed worlds and a galaxy of hundreds of billions of stars, that question still doesn't have an answer. The silence hasn't been broken. No probe has been found sitting quietly on an asteroid. No infrared glow from a Dyson sphere has ever shown up in a survey. No biosignature has survived the kind of rigorous, independent scrutiny that separates a real discovery from an exciting but ultimately unconfirmed signal. The way K2-18b's tentative hints of dimethyl sulfide have been challenged and re-challenged by scientists determined to get it right rather than get it first. And the WOW signal, the single strongest candidate humanity has ever recorded for an artificial transmission from beyond Earth, remains exactly what it was on the morning after it was detected, 72 seconds long, never repeated, and permanently unexplained. Maybe that changes tomorrow. Maybe a spectrometer somewhere catches an unambiguous biosignature that survives every round of scrutiny scientists can throw at it. Maybe Europa Clipper's instruments detect an organic molecule in a plume of water vapor that simply shouldn't be there without something alive producing it. Maybe Breakthrough listens radio dishes, sweeping across 1 million stars with a sensitivity fine enough to catch a single household light bulb burning 25 trillion miles away, finally pick up something that repeats, something that doesn't fade into the same permanent silence the WOW signal did. Or maybe none of that ever happens, not in your lifetime, not in the lifetime of anyone who will ever live, and the silence simply continues, unbroken, for as long as anyone from Earth remains around to keep listening to it. Until one of those two outcomes actually happens, the possibility stays open, sitting quietly underneath every calculation, every equation, and every telescope pointed at the dark, that when we look out at the space between the stars, searching for some sign that we're not the only ones who ever wondered about any of this, the only ones looking back is us,